Hello and welcome back again. So this is the next installment of the public exam review, final exam review for Calculus 3208 from CDLI. And so today we're looking at our last installment on limits and continuity. And we're still in our second unit, which is the first chapter of the essential calculus text. So we're going to look at finding and identifying discontinuities today, but we're not going to do that based on graphs that are given. We're going to actually start from the equations and see where we can get with those. So let's look at what we're going to focus on first of all today, and we're going to look at determining all discontinuities for a given function, and we're going to look at characterizing discontinuities, so all those that we find, into one of our categories that we discussed in a previous session. Okay, so we'll start here with three examples or exemplars, and for each of these we're going to talk about the type of discontinuity that we see and what's sort of creating that or what's causing that to happen. Okay, so the first one that we have, we're given a function here, and the function is given as f of x right over here equals x squared minus x minus 6 divided by x minus 3. So you should be aware, or let's at least review that little bit of our knowledge now, that when we go to graph any rational function, it's a good idea to start by writing it in factored form. So if I factor this equation, the numerator becomes x minus 3 times x plus 2, and our denominator here is x minus 3. And when we do that, what we can see is that canceling these two factors, this function is actually just equal to the linear function x plus 2. But we have to make a little note here. It's not quite x plus 2, because when x is equal to positive 3, this denominator is going to give us headaches. We're going to be undefined. So we have to state the non-permissible value here of x, which says that x is not allowed to be equal to positive 3. So if we think about what the graph of this function will look like, for this function right here, it's going to be exactly the same thing as y equals x plus 2, the linear function, except we're not allowed to exist where x equals 3. So y equals x plus 2 is a linear function, so it's going to have a y-intercept at 2, and it's going to be a straight line. So let's draw a nice straight line for this graph, and we've got to have a positive slope of 1. So a slope of positive 1 is going to give us a graph that looks more or less like this. So we could draw that linear function. But remember, that's not quite correct, because at the point where x equals 3, we've got some trouble with this one. So we go over to where x equals 3 and up to our graph, and right here we have to punch a little hole in our graph and put an open circle. So that point there can't be colored in at all, so that's not shaded. That's an open circle, and what we say about that is that that's one of our first two types of removable discontinuities. So one way that can show up in the equation is if we actually have a rational function where we have the only factor in our denominator that cancels out, or any factor in our denominator canceling out with one from the numerator, and what that gives us is it gives us this little hole in the graph. There is another way that we can encounter a removable discontinuity from an equation for a function. So let's look at this example. This function that we're given here in our second one down here says that f of x is a linear function, x minus 1, as long as x is not equal to 2. And it's equal to exactly 3 when x is equal to 2. Well, that's kind of a funny thing, but piecewise functions are one of the types of functions where we see all kinds of really weird and wonderful discontinuities here. So let's graph that function first of all, where x minus 1 is our equation. So we're going to have a y-intercept at negative 1. And again, we have a positive slope of 1, and I'm going to be a little more careful about the way I draw this one. When I draw this graph, I'm going to draw a line with a slope of 1, but before I get to 2, where x equals 2, I'm going to leave a little space there. So I'm just going to draw it like that, and then I'm going to deliberately break the graph, jump over a full unit, I'm going to jump over just a little spot right there, and then I'm going to keep going on with the slope of 1 again. So the graph looks approximately like that. I'm not drawing this very accurately here, as you can see, but that's kind of irrelevant. The important thing is we see that we're going to have a little hole in the graph right here, so it's broken up right there. And the other thing is, it doesn't mean that we don't have any value at all where x equals 2. They're deliberately telling us that the value of y when x equals 2 is going to be up at 3. So we go all the way up to 3 here, and we put a dot. So that's another type of removable discontinuity. The point has been removed from here, and it's been replaced up there deliberately by design in this piecewise function. So those are two ways that we get removable discontinuities. The third type, or the second type we have here is a jump discontinuity. And there are lots of different ways we can get those. We can get those with certain step functions, we sometimes call them, like the greatest integer function. But most commonly, we see jump discontinuities defined by piecewise functions as well. So here we have a piecewise function that's defined on two different intervals. X is less than 1, or it's greater than or equal to 1. So the first one is defined with a slope of 2 and a y-intercept of -1. It's linear, of course. And it goes up until x is going to be equal to 1, and that's where it kind of disappears. So if we were allowed to have x equal to 1 in that equation, we'd have 2 times 1 minus 1, which would give us a y-coordinate of 1 as well. So the point 1, 1 is going to have to be where this function disappears. And so it's a linear function with a y-intercept at -1. So let's plot that on there. And then we're going to draw a line with a slope of 2, but that line with a slope of 2 is going to have to disappear right before we get to the point 1, 1. So right about there, it's going to be broken up. And so we're going to put a little open circle there to indicate that that point is not included as part of this graph, or at least not that section of it anyway. Then we'll look at the next part. So at every point, including 1 and to the right of it, we're going to follow the equation y equals -x plus 3. So that has a y-intercept up at 3. So we could imagine where that would be, although we're not actually going to plot that y-intercept because the y-intercept is not part of the interval that we have here if we're only to the right of 1. But what we'll do is we'll plot the point that we're allowed to have here at x equals 1. So at x equals 1, we could see that the value here would be -1 plus 3. So we'd be at +2. And then from there, we have to follow a slope of -1 going downward. So I'm going to draw a line from there with a slope of -1 that takes us downward from there. So the graph would look more or less like that. So we have here a linear function that comes up from the left in this direction, goes down to the right in that direction, but we're broken up right there. And so our left and right limits wouldn't be the same, and therefore we have this jump discontinuity at that point. Notice that I didn't include a graph here excuse me, for infinite discontinuities, because we should remember that those are graphs that give us vertical asymptotes. And in the next unit, or a later section of this unit, actually, when we talk about limits involving infinity, we'll get into great detail about how we find vertical asymptotes and characterize them. So we will review that later on, but we're just going to leave it out for now because all the infinity business is still coming down the pipe. Okay, so let's take a look at an example. It says, using the definition of continuity, identify all points at which our function here is discontinuous, and classify those discontinuities as removable or non-removable, or jump, as we're going to call them, for non-removable here because we're not going to have infinites. So first I want to look at the first definition we have here, and that is a quadratic divided by a linear. It's a rational expression. So let's look at that in factored form and see if it helps us at all. So if I factor that out, I'm going to have x minus 2 times x minus 1 in the numerator, all divided by x minus 1 in the denominator. So when x equals 1, we're going to have a point discontinuity. So this first interval, up until we get to where x equals 3, is going to be a linear function with a slope of 1 from this part right here, and a y-intercept at -2. So let's put our y-intercept here. We're going to have a linear function with a slope of 1, only we have to disappear at the point where x equals 3. So the graph is going to look more or less like that, and just disappearing on us at the end there. So then what we'll do is we'll put a little open circle to indicate that that point right there is not actually included. Now it's possible, based on something that we get later on, that we are going to end up including that point, but we'll see what happens. Then the next section that's given for us is, it says the function is equal to a y value of -1 when x is exactly 3, but only at exactly 3. So when x equals 3, y equals -1, that's just a point. So I'm going to plot the point 1, -3 right there. And then the last bit says when we go from +3 and onward, but not including the +3, we follow the line y equals -x plus 5. So let's see where that would be at 3, and we'll draw an open circle there. So at 3, that would be -3 plus 5, which would be at +2. So when x equals 3, that would be up at +2, but we're not actually allowed to include that point. So we'll leave an open circle there. And then what we have to do is follow this on a slope of -1 downward and to the right. So the graph is going to look like this from that point onward. Okay, so our job now, as the question asks, and once we've seen what's happening here, is we have to identify all of the discontinuities and identify the type of discontinuity we had, or classify it. Well, there's only really one place where this graph falls apart, and that's at x equals 3, if we look at it from there. But we have to remember that way back in the beginning, when we first graphed this, we said that the first bit was a rational function, but we also said that x is not going to be allowed to be equal to positive 1. So when x equals positive 1 over here, by rights, we should have a hole in the graph right there as well. So there should be nothing inside that hole. It should be right there. So what we can say is that our left and right limits are the same at x equals positive 1. And since those left and right limits are the same at positive 1, then we're going to have a removable discontinuity there. So let's make a list of our 2 points. When x equals positive 1, we have a removable discontinuity. Oops, pardon my handwriting. And when x equals positive 3, what we have, we can clearly see over here that that's a jump discontinuity. So that one is a jump. We have to go from one place to the other. It's true that this point here has been removed and placed elsewhere, but it's still a jump in the actual graph. So we've got 2 points here. One at x equals 1 that's removable because of the factor that canceled out, and we've got one at x equals 3 that's clearly a jump discontinuity. Okay, let's move on. Here's a test type question, and it's kind of the same thing. Using the definition of continuity, now we have to identify all the points at which f of x is discontinuous. We have to classify them as removable or non-removable. So let's make a quick sketch. We've got 3 different intervals to cover here. The first interval we have to cover is when x is less than 0, and we've got from 0 up to 1, and then we have from 1 and onward. So let's make a quick graph, and that'll help us have a picture of what's happening for this particular function. So the first place we're interested in looking at this graph is sort of everything to the left of 0. That's my first interval. So for everything to the left of 0, we follow the line y equals x plus 2. So on my graph, I'm just going to make a real quick rundown of what sort of my axes will represent here. So let's go, I don't know, 1, 2, 3, 4, 5 units up that way. And again, this doesn't have to be accurate as long as we can identify what's happening for the types of discontinuities. So there's -5 down that way. And then we'll go 1, 2, 3, 4, 5 units that way. And we'll go 1, 2, 3, 4, -5 units all the way over here. So that's -5 units that way. Okay, so we're going to follow the line y equals x plus 2 up until we get to 0. So that would have a y-intercept of 2 if we were allowed to have one, but that's the place where things are going to break down on us. But that is a straight line with a slope of 1 that goes up to there. So there's the first portion of this graph. The second one is y equals 2x squared. So 2x squared is the basic parabola that's been stretched up a little bit. So let's see, 2x squared from 0 up to 1. So let's see what's going to happen with that one. So if we follow 2x squared from 0 to 1, so then we're allowed to include the 0. So at 0, that's equal to 0. And at 1, it's going to be equal to 2. And we're allowed to include that one as well. So this has to look kind of parabolic to go from one of those places to the other, including both endpoints. And then the last one we have starts at x equals 1, and it's going to have a y-coordinate that would be at about +1, although it's not included. So a +1 there, we'd have to have a hole in the graph, and then it's got a slope of -1, so it moves down this way. I should really draw that one with a proper line, although it doesn't really matter a whole lot here. So let's get that out of there, and we'll draw it with a proper line, and we'll see that this graph is going to move down this way. Okay, so I'm going to fix up that little bit of parabolic business in there too, because I bent that a little too much to make it look neat. See that these 2 points should be one right on top of the other where we're discontinuous there. So that's our parabolic bit there. Okay, so right here we can see that we have a jump discontinuity because the left and right limits are not the same. And at 0, we also have a jump discontinuity because our left and right limits are not the same. So at x equals 0, we have a jump. And if we want to state that in terms of the definition, it's because the limit as x approaches 0 from the right of f is not equal to the limit as x approaches 0 from the left of x, or f of x, sorry. Alrighty, so we've got that. And at x equals 1, same story. So x equals 1, we have a jump. and for the exactly the same reason that we had above. Okay, so there's looking at a piecewise function, breaking it down, sketching its graph, and getting an idea of where things are breaking down on us here. Okay, so let's move along. Now is the your turn question. So it's very similar to what we did in the last one. Use your graphing skills to get a graph. Everything is nice and linear, so it shouldn't be too bad to graph. So I'm going to flip to the solution. And there's the solution for the your turn question. So have a look through that to make sure you did everything correctly, and then we'll quickly highlight some of the key points that we saw here. So some of the key points we saw, we identified discontinuities of a given function by looking for specific characteristics that violate the definition. So those things, limits left and right, function not existing, or the two not being equal. And removable discontinuities are found by looking for cancel factors. That was the first place that we saw a removable discontinuity, when we get cancel factors in a rational expression or by design. So if we have a piecewise function where a function has been deliberately removed, then we can get that. In either case, the limit exists, but it's not equal to the value of the function. Jump discontinuities are created by disjoint piecewise graphs. So we have disjoint piecewise graphs. Sometimes we see them with other special functions like the greatest integer function. And either of these can create the same condition if it's jump, left and right limits, not the same. And last but not least, infinite discontinuities, of course. We didn't look at them much here. We just know that they're vertical asymptotes. But when we look at limits involving infinity, we'll get into more detail on that. Okay, so I hope that's helpful in some way, and I hope your studying is going well, and all the best on your exams.